Hi, and welcome to Geeks for Geeks. Today, we would be discussing the problem brain game. Now, in this problem, we are having two players A and B, which take turns alternatively to play a game in which they have n numbers, okay? Like suppose 3, 1, 2, 3 on a paper. And in one turn, a player can replace one of the number by one of its factor except for one and the number itself. Like, suppose we have 6, then 6 can be replaced by its factor, like suppose 2 or 3. But 6 can't be replaced with 1 or 6. This is not possible. A player who is unable to make a move loses the game. Suppose I start and I am able to make a move, but the next person is not able to make a move, then he would lose the game. And the winner of the game A, and both play optimally. This means that there won't be any partiality, that one person is not using his full capacity, but both players would take the right decision at the right time. There won't be any partiality. Okay, fair enough. They would give their best, in short. Okay, now let us look at the very first given sample test case. We have 5, 7, and 3 itself. So, 5, if we look at the factors of 5, we have only 1 and 5 because it is a prime number. Same goes for 7. It is 1 and 7. In the same way, if we go to 3, then it is given by 1 and 3. Okay, so we don't have any number which have any factors other than the number itself or 1. So, the first player who starts the game, it is telling us if A starts the game. If A would start the game, he would try to replace it with the factors, but there exist no factors. So if A is not able to make a move, then B would be the winner. Now let's take one more example where we can do some operations. So first we would find the factors. If we talk about the factors of 2, then it is 1 and 2. If we talk about the factors of 4, it is 1, 2 and 4 itself. If we talk about the factors of 7, it is 1 and 7. If we talk about the factors of 11, it is 1 and 11, because apart from 4, all are prime numbers. Okay. So if A would come, what he can do is he can only replace it with this. Why? Because other than this is the number itself and this is 1. Number itself and 1. Number itself and 1. So he can't replace with that. So 4 can be only replaced with 2. So he would replace 4 with 2. And in the next move, for B, there is no remaining factor. So B won't be able to make a move and A would win itself. Okay, this is how the explanation works. Okay. So now, before talking about the solution or before talking about the intuition, let us talk about an idea from game theory. Okay. That is known as Nim Game. So, Nim Game is a very famous game in which two players take turns removing items from distant piles. Like, suppose we have 5, 4, 3, 2. Okay. So, this is the piles. Okay. And in each turn, you can remove either 1, either 2, either 3, either 4, or either 5. Okay. And the player must remove one or more items from a single. Like he can remove one or more items from the non-empty. And if it becomes non-empty, suppose we remove all the 5, then it becomes empty. So we can't remove from here. And the winner of the game is the one who removes the last item from the last non-empty file. Okay, simple thing. So here it is just telling us that the winner of the game is the one who would be who would be able to remove the last file. Same as this one. Like he is telling us that the person who is not able to make a move loses the game. Same way, just a different way. Like एक में अगर हम मूव नहीं कर पा रहे हैं तो वो हार जा रहा है और नेक्स्ट पर्सन जीत जा रहा है और जो लास्ट मूव करेगा वो जीतेगा सेम थिंग बट इन अ डिफरेंट पोर्ट्रेड इन अ डिफरेंट मैनर फेयर इनफ लेट्स मूव फॉरवर्ड so now in this so if we are playing this game then there is something known as Nim Sum. Okay, there exists something known as Nim Sum. Nim Sum tells us that we need to find the XOR of all the numbers. Suppose we have the elements as 1, 2, 5, and 7. And this can be written as A1, A2, A3 and A4 of the array A. So Nim sum is nothing but A1 XOR A2 XOR A3 XOR A4, which is equal to 1 XOR 2 XOR 5 XOR 7. And if so, Nim sum tells us that if the value is equals to 0, then A won't be able to make a move, and A won't be able to make a move at the end. Or we can say the same thing if you want a better understanding, that B would make the last move. Okay, A won't be able to make a move at the end, or B would make the last move. If B would make the move, then A would win. If A would make the last move, then B would win. If the value is 0, then B would win. Nim sum tells us this. If we do the XOR of all the elements, and if we generalize this, then this becomes, okay, this becomes A1 XOR A2 XOR A3 XOR till the value of AN minus 1. If it is 0 index, if it is 1 index, then it would be from 1 to n itself. Okay. Now, if the value is not equal to 0, if the value is not equal to 0, then the last move would be made by A. Okay. A would make the last move. A would make the last move. This is what you can do. Fair enough? So now, if you look at this problem, then this problem is kind of very similar. That we are taking out factors and we are removing factors till we have 0 factors left. Okay, we are removing factors till we have 0 factors left. And when we stop, when the number is a prime number, that means it has only 1, and the number itself, that is for 11, we have only 1 and 11. So the same kind, this problem is just an application of Nim Game. Okay, or you can call it a variation, not properly a variation, just in a different manner. Okay, just covered with it. Fair enough. So if somehow we find the number of factors we can remove apart from 1 and itself, and we keep it somewhere, then we can use the same approach that we would find the Nim sum. If the value is 0, then A would lose and B would win. If the value is non-zero, then A would make the last move and A would win. Okay, we can use this or not? Yes, definitely we can use this. So now the problem arises that we just need to find the factors apart from 1 and itself. And we don't even need to find the factors. We just need to find the number of factors. Find the number of factors. The number is enough. So now to find the number of factors, we can use the approach of prime sieve. Okay, like we would start from 2. Okay, the same idea. What is prime sieve? In the prime sieve, we assign, so suppose let us quickly discuss about prime sieve. Okay, so what is the basic idea of prime sieve? Let us draw a 5 into 5 matrix, and you would get a proper. Let us enumerate this also. So 1, 2, 3, 4, and 5, 6, 7, 8, 9, 10. Then we have 11, 12, 13, 14, and 15. We have 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25 itself. So now what we do is, initially we start off, go to 1 and say it is not prime. Then we go to 2. Till now we are marking everything as prime. Initially we would mark everything as prime, and we would explicitly mark 1 as not prime. अलग से 1 को not prime mark कर देंगे, सारे को prime mark कर देंगे. And then we would start the iteration. We would go to 2. Till now 2 has survived as a prime number. So all the multiples of 2 would be a non-prime number. Okay. So we would composite number. This is a composite number. 2 multiplied by 2, 2 multiplied by 3, 2 multiplied by 4, 2 multiplied by 5, 2 multiplied 6, 7, then 8, then 9, then 10, then 11, then 12. And these are not prime. Now we go to the value 3. 3 has survived as a prime number. So the multiples of 3 should be marked as a composite number. 3 multiplied by 2 is 6, which is already marked. 3, 9 not marked, so we would mark it. Then 12, which is already marked. 15 not marked, so we would mark it. And then we have 18, which is already marked. 21 not marked, so we would mark it. And then we come to 24, which is already marked. Then we would go to 5. Because 4 is marked as a composite number, so we would simply ignore and move on. We would go to 5, and then we would mark 10. 5 multiplied by 2, 5 multiplied by 3, 15, then 20, and then 25. Apart from 25, everyone was already marked by this time. 6 is already marked, so we would simply ignore that. Next, we would go to 7. 7 multiplied by 2 is 14, which is already marked. 21 is already marked, and 28 is out of this range. Then we go to 11. 11 multiplied by 2 is equals to 22, which is already marked. Then we go to 12, which is already marked, so we won't do anything, simply ignore and move on. Then we go to 13. 13 multiplied by 2 is out of this range, so we won't talk about it. 14 multiplied by 2 is out of the range and it is already marked, so we won't ignore, simply ignore, ignore. 17, 34 is out of this range, ignore. Okay, 18 out of this range, 19 out of this range, 20, ignore, 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 out of this range, ignore, out of out of this range, ignore, ignore. This is what we would do. And after this time, you would see that we have found out all the prime numbers in the range this from 1 to 25. And the same idea we would use to find the factors. Okay. So what we would do is, if we are going to 2, initially we have the marked as 0. We would mark everyone as 0. We would initially mark everything with 0. I would just tell you the idea and then we would implement it so that you would get a proper hang of it. Okay. So I would simply draw it once more. So we have 0. So we have the values as 1, 2, or let's start from the 2 itself. 2, 3, 4, 5, 6, 7, 8, 9, and 10 itself. Separated them by comma. So what we would do is, initially we would mark all the factors as 0. The number of factors initially for everyone is 0 itself. Then we would go to 2. Okay. Then all the multiples of 2, we would say that the number of factors you have, okay, and the number of factors 2 have plus 1. Why? Because the number of factors 2 plus 1 again, we can do that. So which is greater? Max of what is already there. 4 already has 0 and 2, that is 0 plus 1. Why? Because that is 2 multiplied by 2. That is 0 plus 1 is equals to 1. Which is greater? 1 is greater. So we would update it to 1 itself. Okay. And then we would go to the 6. And then we would do the same thing. 0, 1, update it to 1. Update it to 1. Update it to 1. Then we would go to 3. 3 multiplied by 2, that is 6. So 0 plus 1, it already has 1, 1, 1. Now it would be kind of like this. 1, because it already has 1 and 0 plus 1 is equals to 1. So we would simply say that 1, 1 is equals to 1. Then we would go to 6. After that, it would go to 9. 9 is equals to 0, 1, which is greater 1. So we would simply update it to that. Then we would go to 4. Then the multiple of 4, okay, that is 4 multiplied by 2 is equals to 8. So we would say that max of 1, number of multiples already 4 has, plus 1. Why? Because 4 multiplied by 2, that is 8. So which one is greater, 1 or 2? Obviously 2 is greater. So we would update the value of 8 as 2 itself. Then we would go to 5. 5 multiplied by 2 is equals to 10. So 0 plus 1, 1. Max of 1 is equals to 1. So this is how we can find the number of factors. So yes, see, 2 can't be reduced prime number, 3 can't be reduced prime number, but 4 can be reduced to 2. But there is no other way we can reduce it. 5 can't be reduced because it is a prime number. 6 can't be reduced. So see, 6 can be reduced by 3. After reducing by 2 or by 3, we would have the value. If we reduce by 3, we would have the value 2, which is the prime number. If we reduce the value by 3, then we would have 2, which is a prime number. And 7 is a prime number, so we can't reduce that. 8, we can reduce it by 4, and then we can go to 2. We can reduce that. 9, we can reduce it, divide by 3, and we can have 3 at the end. Then we have 5. Either we can reduce it by 2 and have 5, or 5 and then have 2. We can do either of them, not both of them. So if you do this on a pen and paper, you would see, okay, just do a dry run on a pen and paper from 2 to 10 and you would have the hang of it. So this is how we can find the number of factors. Okay, so now let us go to the implementation and you would see that. So let us sum up everything before implementing. What we would do is we would first find the factors by using this method. We would initially have 0 and then we would start from 2. Okay, and then we would say that max of the number 2 or the multiple of that, and we would find the number of factors. The number of factors, we would do a XOR of it. If the value is 0, then we would say that if the value is 0, then B would make the last move. That means B would win, else A would win. Simple thing. So now let's start the implementation itself. So what we would do is we would start with the vector of int of A, and we would simply calculate the values of all because we have till 1000. So we would go to 1001 and initially we would assign everything with 0, or you can simply take here 0. But initially vector have the value as 0, no garbage values. So then we would start off int I is equals to 2, I is less than equal to 1000 because it is still 1001. So we would go till 1000 or less than 1001, less than equal to 1000 or this. Okay, and then we would go down and we would say that for int j is equals to 2 multiplied by the value of I, and j is less than equal to 1000, and then j plus equals to I. Now let me quickly do a dry run of this thing. What would be the values of j? So if I is equals to 2, suppose I is equals to 2, then j is equals to 2 into I. That is 2 multiplied by 2 is equals to 4. Then the next time j plus I, that is j plus 2, and the next value would be 6. And the next value would be 6 plus 2, that is I. Next value would be 8. Then we have 10. Then we have 12. Then we have 14. This is how we would get all the multiples of it. Okay. First we would multiply it by 2 and then we would keep incrementing by the number itself. Suppose we have 5. 5 multiplied by 2, 10, and then we add 5. Then it will be 15. 15 plus 5, that is 20. So we would keep doing that. Okay. Now A of j is equals to max of A of j itself first, whatever the value is already there, and then 1 plus A of I. Because now this time we can 5 multiplied by 2, that is 10. So yes, we can have a factor. This is what we are doing. Then we move forward and we would initialize x is equals to 0, so that we would keep the XOR value here. And then we would initialize, or int I is equals to 0, I is less than, or int I is equals to 0, I is less than nums dot size itself, and I it's I plus plus. You can simply do a for each loop also, which would make the implementation a little bit small. And x is equals to x XOR A of num of I. Okay, nums of I itself. Then if the value x is equals to 0. So I told that if x is equals to 0, then B would make the last move. That means B would win. So we are told that if B would win, then we need to return false. So we would simply return a false value. Okay. Else we would return a true value. Okay. Let us quickly compile this and see if we can get get a correct output for the sample test case or not. Okay, fair enough. We are getting a correct output for the sample test case. Now let us submit this and see if we can get an AC or not. And yes, we got an AC. How you would solve this? It revolves around the idea of Nim Game. So you need to first know the Nim Game and the variations of it, and then this is an application of Nim Game. So you can tell that game, the basics of game theory or the Nim Game is a prerequisite of this problem. That's it for today. Thank you and have a nice day. If you face any difficulty regarding the understanding of this problem, feel free to raise your doubts in the comment section.